We've got two vectors here, v and w, written in column vector notation and also I hat and j hat notation. With the column vector notation, it is important that you put the first component in the top and the second component in the bottom. That is important. If you swap those around, you get a different vector. With the I hat and j hat notation, you don't have to put the I hat term first and the j hat term second. I could write this as 3j hat plus I hat, and it's the same vector. I could write this one as 2j hat plus 4i hat. It is important that, like for this example, the 3 goes in front of the j hat and the 1, which I didn't write, goes in front of the I hat. That is important, but it doesn't matter which order you write them in. Here again, in column vector notation, it does matter. First component, or component if you prefer, 1, second component 3 for v means that if I graph v to start at the origin, the first component is 1, the second component is 3, means the tip of the vector or head of the vector is at the point 1, 3. So this would be the vector v drawn as an arrow. I'm assuming most of you are at least somewhat familiar with vectors and vector notation. Little half arrow above the vector. Why not a full arrow? It's just because we're lazy. Some people draw the half arrow the other direction. It doesn't matter. Some people draw a full arrow. It doesn't matter. Some people even draw the arrow or line under the vector instead of above it. Wildly different notation for vectors. W has components 4, 2. First component 4, go over 4. Second component 2, go up 2. We got to end right about there. There's W. To find the components of v plus w, it's very simple. You just add component-wise. V plus w is going to have first component 1 plus 4 and second component 3 plus 2. 5, 5 are the components of v plus w. In I hat, j hat notation, that's 5i hat plus 5j hat. For the subtraction, v minus w, you subtract component-wise. First component, 1 minus 4. Second component, 3 minus 2. Giving you -3, 1. How do you draw these in here? Well, you could put them so that their base, their tail, is at the origin again. And I will do that for v plus w, but I'm not going to do it for v minus w. You have freedom with vectors to move them to different spots. As long as you get the direction and length or magnitude right, it's the same vector. It's just a convention. It's a convenient convention to allow that. So I could certainly just draw right away v plus w to have components 5, 5, which if I put its tail at the origin, means its head is going to be out here, right about there. That is v plus w. As far as explaining the geometric interpretation of this, there's a couple different ways of doing it. You can take v and translate it so that its tail or starting point is at the head of w. The tip of w is called its head. The starting or base point of v is called its tail. I can translate it here to start or have its tail at the head of w. And if you've drawn things accurately, its head will be at the right point. Right there. That is also v. It doesn't look so perfect because I can't draw perfectly here. But it's supposed to have the same direction and length as the original red arrow, even though it doesn't look exactly right. Okay? Because drawings are not perfect. So you could think of v plus w as the vector obtained by first going along w and then going along v. And then drawing an arrow to start at the original starting point and end at the final ending point. There's also something called the parallelogram law. You can also translate w to being up here. To create a parallelogram, And V plus W, yes, is the diagonal of the parallelogram. V minus W is a little trickier to interpret. There's really a couple different ways to do it. One way to do it is to say, okay, I've got V here and I've got W there. Let me also draw in negative W as an arrow. The opposite of W, which as an arrow is going to have the same length of W, but pointing in the opposite direction. I didn't really give myself quite enough room in the picture here. Negative W is going to have components -4, -2. It's going to look about like this. And realize that you want V minus W. That should be the same as V plus negative W. And so effectively now I can use the parallelogram law on a new parallelogram. That's going to look about like this over here. And then V minus W is going to go be this diagonal right there. So V minus W, which has components -3, +1, that looks right, is going to be that arrow right there. Another way to view V minus W, probably the more common way because it's quicker, is to say V minus W is the vector that when I add it to W, it gives me V. Because the W's would cancel. So I go back to the original two vectors, this red arrow right here, and this green arrow right here, and I ask myself, what vector, when added to W, will give me V? What arrow can I put at the head of W, whose new head will be at the head of V? An arrow like this. And you can see that these two vectors look like they are the same length in parallel, if I drew it perfectly. There's V minus W as well. That's a vector that when added to W gives you V. Okay? That was very quick. And as quick as I could, brief explanation of vector addition and vector subtraction. I did it quickly because I'm assuming most of you have learned about vectors before. You just need reminding. If I was teaching about vectors from scratch in this kind of way, I would have tried to go 2 or 3 times slower. Okay? If this is feeling still unfamiliar or new to you, it's something to continue working on. If you're real experienced with vectors, don't forget this. It's important still. And there's plenty more to learn about vectors that you may have forgotten or you need refreshers on. Okay? So it is still worth paying attention to the lectures.